Hello, welcome to another module in this massive open online course. We are looking at the Z transform, its properties and applications. Let us continue this discussion. Today let us look at the convolution, right, how to implement or what is the property of the Z transform with respect to the convolution operation. Okay. So, start by looking at convolution. Remember, the convolution of two discrete time signals can be defined, that is, let us say we have two discrete time signals x1 n which has Z transform x1 z, and we have another signal x2 n which has Z transform x2 z. What can we say about y n, which is the convolution of x1 n and x2 n, that is, this is equal to summation, that is y n equals summation m equals minus infinity to infinity x1 n into, or x1 m rather, into x2 n minus m. Now, we have the Z transform of y n is y z, which is given as summation n equals minus infinity to infinity y n z raised to minus n. This is the Z transform of the sequence y n, which is summation from minus infinity to infinity y n z raised to minus n. We want to find out what is the Z transform of y n when y n is the convolution, that is convolution of two signals, discrete time signals x1 n and x2 n. Okay. And therefore, now substitute the expression for y n from above. This is the expression for y n, correct, and substitute the expression for y n from above. So, I have summation, let me just write it clearly. So, this is equal to summation n equals minus infinity to infinity summation m equals minus infinity to infinity x1 m x2 n minus m z raised to minus m. Okay. So, this part, if you remember, this part is y of n. So, summation n equals minus infinity to infinity y of n z raised to minus n. Now, I am going to interchange the order of summation. So, I am going to write first m equals minus infinity to infinity x1 of m summation n equals minus infinity to infinity x2 of n minus m z raised to minus n. Okay. So, this is basically by interchanging the order of summation. Interchanging the order of the sum, and now you can see this is the Z transform of x2, that is x2 n minus m, that is x2 delayed by m. So, this is Z transform x2 n delayed by m, and therefore, this is nothing but x2 z into z raised to minus m, and therefore, I can now write this as summation m equals minus infinity to infinity x1 m x2z into z raised to minus m. Now, the x2z comes out common. So, this is x2z summation m equals minus infinity to infinity x1m into z raised to minus m, and this you can clearly see this is x1z. So, this is basically the product of the z transforms x1z into x2z. So, what we have here is basically yz equals x1z to x2z. So, the z transform of the convolution of two signals is basically the product of their z transforms, and this is similar to what we have seen in the Laplace transform. That is, when you convolve two signals in the time domain, in the transform domain their Laplace transforms are multiplied. That is, the Laplace transform of the convolution of two signals is basically the product of the individual Laplace transforms. Therefore, similar to the Laplace transform, this property gives us a convenient way to implement convolution, because convolution is typically fairly intricate to evaluate. So, one can otherwise as a trick evaluate the z transforms of the signal, multiply the z transforms and take the inverse z transform to evaluate the convolution. Okay. So, this is an interesting property basically which says that convolution in time is multiplication in the z transform domain. Okay. So, in convolve two signals, the z transform resulting signal is basically the multiplication of the z transforms of the signals being convolved. Let us now look at techniques to evaluate the inverse z transform, and similar to the inverse Laplace transform, one can consider one of the simplest techniques, that is by partial fraction expansion. Okay. So, let us say we have xz equals summation n equals minus infinity to infinity xn z raised to power of minus n. Now, let xz, now one thing we can do is, the simplest thing we can do is express xz as a power series. Simplest way to evaluate the z transform is to express xz as a power series. Now, once you express xz as a power series, xn is nothing but the coefficient of z raised to minus n. Okay. So, that is one simple way to find the z transform. So, xn, so once you express xz as a power series, realize that xn is the coefficient of z raised to minus n. Now, let us look at another technique, that is, so we can call this as the power series technique. Let us look at another technique, that is the partial fraction expansion. Okay. So, basically you have, let us say xz is a rational function, that is nz divided by dz, that is, this is a rational function of z which I can write as some constant k times z minus z1 z minus z2 z minus zm divided by z minus p1 z minus p2 z minus pn. Now, we know that z1, z2, zm are the zeros, that is roots of the numerator polynomial. These are the zeros, and you have m such zeros, z1, z2, zm are the zeros, which are basically nothing but the roots of the numerator polynomial. Remember, we are assuming a rational function, that is z transform is given by given as a rational function of z. Okay. That is, it is of the form of a numerator polynomial divided by a denominator polynomial. Okay. And p1, p2, pn, these are obviously the poles. Okay. And we have, these are the n poles, and let us assume that n greater than or equal to m. Okay. And further assume all poles are simple. Okay. That is, there are no repeated poles. This implies there are no repeated poles, in which case I can express xz over z, the partial fraction expansion of xz over z is given as c naught over z plus c1 over z minus p1 plus c2 over z minus p2 plus so on Cn over z minus Pn, which can be simplified as C naught over z plus summation k equals 1 to n Ck over z minus Pk, where the coefficient C naught can be found as C naught equals, simply evaluate xz at z equal to 0, and Ck is basically given as z minus Pk times xz evaluated at z equals Pk. And finally, we have substituting the values of C naught, C1 up to Cn, where we have n simple poles we have, and taking the z in the denominator onto the other side, we have xz equals C naught plus C1z divided by z minus P1 plus C2z divided by z minus P2 plus Cnz divided by z minus Pn. Okay. And now the inverse transform can be found, because remember, we know the inverse transform of each factor, which is of the form z minus z over z minus Pi. We know the inverse transform of every such term, and therefore, now forming the z transforms of these individual partial fractions and then forming the sum, that gives us the inverse z transform of this rational function of z. So, we know the z transforms of, for instance, z over z minus P1, z over z minus P2, z over z. So, put these together. So, compute z transforms of these terms. compute Z transforms of the individual terms and then followed by their sum. Okay. So, that gives us the inverse Z transform. Now, if Xz has multiple poles, if Xz if Fz has poles with multiplicity greater than 1, that is imply, let us say example Pi of pole Pi of multiplicity equals R, correct. Multiplicity means multiplicity greater than 1 means repeated poles, that is you have terms of the form Z minus Pi square multiplicity of 2, or multiplicity of 3 implies Z, you have a term of the form Z minus Pi cube, that is pole Pi has multiplicity of 3. Okay. So, in that scenario, if you if let us say pole Pi has multiplicity R, then Xz over Z will have terms of the form each such pole Pi with multiplicity greater than 1 will contribute to terms of the form lambda 1 by Z minus Pi over lambda 2 by Z minus Pi square plus lambda R over Z minus Pi raised to the power of R, where this quantity lambda R minus k equals well 0 to R minus 1, this is will be given as 1 over k factorial d raised to k over dz to the k Z minus Pi raised to the k Xz by Z evaluated at, that is the kth derivative of Z minus Pi raised to the power of k times Xz over Z evaluated at Z equals Pi. So, this is the expression for lambda R minus k. Okay. So, this is the expression for the term lambda R minus k, which basically there is a coefficient of the term Z minus Pi raised to the power of R minus k. Alright. So, we have lambda 1 over Z minus Pi, lambda 2 over Z minus Pi square, so on and so forth, lambda R over Z minus Pi raised to the power of R. The coefficient lambda R minus k is 1 over k factorial d to the k, that is d raised to the power of k over dz k Z minus Pi to the power of k Xz over Z evaluated at Z equal to Pi, that is a kth derivative of Z minus Pi raised to k into Xz over Z evaluated at Z equal to Pi. Okay. And from this once again one can find the inverse Z transform of the given function. Let us now look at the properties of the region of convergence, the properties of the ROC . The properties of the ROC are as follows. Number 1, ROC does not contain any port 2 if x n equals a finite implies that x n equal to 0 for either x n equals 0 for n less than n 1 or n greater than n 2. That is, it is non-zero only in the interval n 1 to n 2 and x z converges for some value of z x z converges for some value of z, all right, then this implies that ROC equals the entire z plane. So, the point is that basically if you have a finite sequence, that is if the sequence is not infinite, it is a finite sequence, it exists only in a finite region, that is it exists only in the finite interval n 1 to n 2, that is 0 if n is less than n 1 or 0 if n is greater than n 2 and it is non-zero only in this interval n 1 to n 2, then basically the z transform of that signal, that is a finite signal, exists everywhere on the z plane if it converges for a single point. If it converges for any single point, it exists everywhere on the z plane, that is the entire z plane. Okay. Now, for a right handed signal, again this is something similar to the Laplace transform. For right handed signal, now right handed signal implies that x n equals 0 that is there exists some n 1 that such that x n equals 0 for n less than equal to n 1. Now, this implies for a right handed signal ROC is of the form magnitude of z, that is ROC is of the form magnitude of z greater than R max, where R max equals the magnitude magnitude of the largest or largest, this is the largest magnitude of the poles of x of z. So, R max is the largest amongst the magnitudes of the poles of x z, and if it is a right handed signal, then the ROC has to be, if it is a right handed signal, then the ROC has to be of the form magnitude of z greater than R max. Now, similarly for a left handed signal, now what is a left handed signal? Once again, a left handed signal is if x n equals 0 for some n greater than or equal to n 2, that is there exists an n 2 such that x n equals 0 for n greater than or equal to n 2. This implies that the ROC is of the form magnitude of z is less than R min, where R min equals smallest magnitudes, that is the minimum of the magnitudes minimum of the magnitudes of poles of x of z, that is magnitude z is less than, that is for a left handed signal you have the ROC is of the form magnitude z less than r min, where r min is the minimum of the magnitudes of the poles of x of z. So, your ROC will be of the form, so if this is r min, minimum of the magnitude of the poles, your ROC will be inside this circle, that is magnitude z less than r min, where r min is the, so ROC will be interior of the circle or the circular region. Okay. So, this is the ROC is of the form magnitude z less than r min. Okay. And finally, if xn is a two sided signal, now if xn equals a two sided signal, that is this is infinite duration from minus infinity to infinity, minus infinity to infinity, then this implies that the ROC is of the form R1 less than magnitude of z is less than R2. Now, R1 and R2, these are the magnitudes of two poles this is of the form R1 less than magnitude z less than R2, where R1 R2 are the magnitudes of two poles of x of so. So, these are the properties of the ROC. Remember, the ROC stands for region of convergence. Once again, I think we have seen that enough times before, so I do not need to go over that again. So, the ROC stands for the region of convergence, and we have seen the properties of the ROC for several signals. That is what happens to the ROC for a finite signal of finite duration, ROC for a left handed signal, right handed signal, and then a two sided signal. Alright. So, these are useful properties of the ROC one has to bear in mind while and this helps us better reconstruct as well as analyze the properties of a signal by looking at this as Z transform of the signal. Alright. So, we will stop here and continue with other aspects in the subsequent modules. Thank you very much.